Alright everybody, what we're going to be looking at in today's video is reflection and refraction. So the first topic, reflection, is a really good starting point for us to look at how light interacts with surfaces and other materials because everybody's got a very good intuition of how reflection works. So the important thing to keep in mind here for reflection is that I'm going to have two angles I'm always working with. The first is my angle of incidence, okay? This is my incoming angle, okay? And then the second is going to be my angle of my reflected angle, right? So this is the outgoing angle. And the important thing for us here is that these things are equal, okay? But these are with respect to normal of a surface. Okay, so this part here is very important. Okay, so with respect to the normal of the surface, right, or the surface itself, these two will always be the same. So what we're looking at here is that I have my light is incident on this plane right here. Okay, so if this light comes in, I want to know what angle is going to leave at. Well, what will happen is it will mirror whatever it came in with. It will mirror that. And then if we compare these angles with respect to the incidence or with respect to the surface here, these are always the same. These angles are always the same. So if it comes in at 30 degrees, it leaves at 30 degrees, right? Pretty simple and straightforward to work with. But this changes, right? This doesn't mean that this angle kind of globally, right, is always the same as this angle. It just means with respect to my surface, with respect to its normal. So if I were to, let's say, take this exact same light ray and now we're going to reflect it on this surface right here. So if I do this, okay, well this changes this angle a little bit and it makes it larger, okay? But I don't end up with, okay, so I'm just going to copy this over so you guys can compare this, see if this works. This will not happen, right? So this is not the same surface. So my angles here aren't the same as they were before, okay? This doesn't work because now my angles aren't equal with respect to my surface. So what actually happens here is that my wave now will look something like this. Okay, so pretty much it just is reflected its angle, but it's with respect to its surface that is reflecting off of, right? So this is just the important thing to keep in mind because if we turn our surface, our reflected angle and our incident angle will change. Okay, so moving on. Now we have our incident and reflect angles. We can also consider this for our theta 1 and our theta 2 as incoming and outgoing angles, right? To make it a little bit more general. So in this case here, we're going to start looking at refraction. So for refraction, what's going to happen is I'm going to have light that's going to travel through something. So not reflect off the surface necessarily, but it's going to now go from one medium to another medium. So in this case, a medium just being a material, something that it's traveling through. So normally here we have, let's say we start with air or vacuum, right? So, you know, having a standard index of refraction, okay? And we'll get to that in a little bit. And then we're going to travel into another medium, something that it has a different material, has different properties. And this is going to affect the way that light travels. So coming in here, we have light coming in from air. Okay, we'll call this air. And it's going to have a certain N value, a certain index of refraction. Okay, and it's going to go in here and then maybe we'll say that this is water. Okay, so these can be any two materials But just so you know, we can look at how light will travel when it goes from air through water. And so you guys may have seen this already, this effect, if you've ever seen something like through a swimming pool, um, or a surface of water, something like this, that the light plays kind of weird when you look at um, something that it's in the air and then also maybe partially submerged in the water, because the light ray will refract. Okay, so in this case here, it doesn't travel in a straight line. What happens is it was traveling in a certain line, and then now it's bent. It still travels in a straight line in water as well, but there's a bending point at this surface. And this is dependent on something called Snell's law. So my index of refraction is going to be a measure of sort of the material that the light is going through, right? And we're going to use this to describe how water moves from one medium through another with Snell's law, which is right here. So this is n1 times sine of angle 1. Okay, so we'll call this my angle. And then n2 times sine of theta 2. And sorry, of course, my angles should be actually out here now, because now it's definitely important that we do this with respect to the normal, okay? Before, we can do this with respect to the normal or the surface either way, because it's the same thing. But now we're going to be looking at how this angle is changing. So we definitely want to make this with respect to the perpendicular of my surface, so that I can call this n1, okay, so sine theta 1 and sine of theta 2. So let's kind of see how this works. So let's say I want to know what will be the refracted angle when my light is traveling from air to water. So let's say air has an index of refraction of 1. We'll make this sort of standard. And then my index of refraction of water is going to be 1.33. So if I come in here at 30 degrees, okay, 30 degrees off of my perpendicular, then what will my angle be now once it's in the water? Well, what we can do here is we can look at my Snell's formula. N1 sine theta 1 is equal to N2 sine theta 2. So this formula is pretty easy to work with. The only thing is getting theta by itself. So what I want to do is I want to work with this formula by itself before I plug anything in, and get theta 2 by itself, just to show you a general way of how you guys can do this algebraically, okay? First, we need to get sine theta 2 by itself, so we'll go ahead and cancel out n2. The next thing that we can do is we can, let's go ahead and rewrite this, sine theta 1, is we can do this, I'll do this here in another color, sine inverse of this. And what will happen is my sine and my sine inverse will cancel. Okay? So we can find here the inverse of this value, the sine inverse of this value, and easily find my theta 2, right? So we can do that right now. So let's go ahead and plug everything in. Let's say sine of 30 degrees, so we've got 1 over 1.33 sine of 30 degrees, and we're going to take sine inverse of this in order to find theta 2. Okay, so my sine of 30 degrees should be 0.5. So I've got 1 over 1.33, half of that, and then the sine inverse of this will give me theta 2 is approximately equal to 22.1 degrees. So you can see here that we start out with 30 degrees from the normal, and then we end with 22 degrees from the normal. So there's two things here that we want to keep in mind. The first is Okay, if N2 is greater than N1, pretty much you're going from a less dense material to a higher density material. It's just a general way to look at this. Then what's going to happen is theta 2 is going to be less than theta 1. Okay, so it's going to bend toward the normal. Okay, if on the other hand, so if N1 is greater than N2, so I'm going from a higher density material to a lower density material. Okay, in this case, my theta 1 is going to be bigger than my theta 2. So this would look something like this, if I were to do this here, where my angle would be larger. Okay, it would be larger than it was before. So this happens, let's say if you're going from water to air, this will happen, right? So this exact backward situation would happen where if I went from 22 degrees in water, it would actually come out at 30 degrees in air, right? We can do this backwards as well. The last thing is that not only the angle of this light is affected, but also the speed or the velocity of light in any of these mediums is affected when you go from something like air to something with a higher density or a higher index of refraction. And the formula that we can use to find this is very simple, which C, remember this is my speed of light, divided by my index of refraction. This will give me my new speed of light in a certain medium, right? So let's go ahead and jump right into an example of what is the speed of light in diamond. Just to take an example, if the index of refraction in diamond is 2.4. So we can do this. So I'm going to call this V diamond is equal to C over 2.4. So remember, this is just 3 times 10 to the 8 over 2.4, right? So if we do this, this is 1.25 times 10 to the 8 meters per second. So first of all, this is still incredibly fast, but it's almost 1/3 of the original speed of light. You're almost going at 30% of the original speed of light just by moving in diamond, right? So we've slowed down light quite a bit by moving through this material right here.